All right, back to the stick people. So now what we're going to do is determine whether or not two different characteristics are independent of one another. And so we'll start with just a simple concept here. Let's say I made the statement that you're more likely to not be wearing shoes if you wear a green dress. So what I'm saying is that whether or not you're wearing a green dress has an effect on if you wear shoes. I think that people who wear green dresses are less likely to have shoes on. So how can I test this theory? Well, what I'm actually trying to say here, and we can use the vocabulary from our last lesson, is I'm trying to say that the probability of not wearing shoes, or in this case I could call that B complement, given you're wearing a green dress, is high. So I think that this is a likely scenario. I think that the probability that you're not wearing shoes, given that you have a green dress on, is really high. Because I think these two events are related somehow. So let's calculate this. What is the probability that I'm not wearing shoes, or that someone in this group is not wearing shoes, given that they have a green dress on? Well, there are 3 people who have green dresses. And of the 3 people with green dresses, how many of them have shoes? None of them. Okay, so remember the question here is how many are not wearing shoes? And all 3 of them are not wearing shoes. So there is a 100% chance that if you're wearing a green dress, you don't have blue shoes on. So I could say that these events are related if I could compare this to something else. Because I don't necessarily know if this is unusual. Maybe if I pick from a different population, I still get a 100% chance of finding someone who's not wearing blue shoes. So what I'm going to do is I'm going to compare this to the probability of someone just not wearing blue shoes in general. And I'm going to see if I get the same thing. Because right now what I'm testing is what is the probability that someone is not wearing shoes given that they're wearing a green dress. And I want to see if that's any different from the probability of just picking someone who's not wearing blue shoes in general. If these are the same, then I'm going to say that these two events clearly are independent of one another because it doesn't matter if you're wearing a green dress, you're still just as likely to be not wearing shoes. But we have to make this calculation first. So now it's not a given statement anymore, so our denominator and the number of possibilities is 10 because there are 10 people here. And of these 10 people, how many of them are not wearing blue shoes? 1, 2, 3, 4, 5, 6. 6 out of 10, which is 60%. So now we've got a conclusion we have to make here. As it turns out, you're more likely to not be wearing shoes if you're wearing a green dress than you are if you're just generally choosing from the population. So because these two things are not equal, and now I'm going to generalize and say, if the probability of some event A given some event B is not equal to the probability of just that event A all on its own, then what you've shown is that these things are not independent. Or you could say they are dependent. And just one more time, I'm going to try to put this into another context so we can understand it better. So what this says is that if I just look at the probability of someone not wearing shoes, there's a 60% chance that if I'm walking around town with these people, there's a 60% chance of choosing somebody who's not wearing shoes. But if I narrow my scope to only focusing on people who are wearing green dresses, that percentage goes up to 100. So the conclusion I can draw from this is that it seems like there is some relationship between not wearing shoes and green dresses, where if you have a green dress on, it makes you less likely to be wearing shoes. And that's just based on this raw data. So the other way around is if it turned out that the probability of A given B was equal to the probability of A, then I would say these are independent events. And I'd be able to say that green dress has no effect on no shoes. These two things don't have anything to do with each other. All right, let's look at another example. So the data in this table represents a sample of 100 people, and they were asked if they are the oldest, the middle, or the youngest child in their family. So let's just assume that every person that was surveyed is a member of a 3-child family, and then they were identified as either being a tall person or a short person. And what the metric was that was used for that doesn't really matter. I don't know, let's say that tall is 6 foot or taller and short is under 6 foot, whatever. Now, my hypothesis is that tall people are more likely to be the middle child. And so what I'm going to do is test this hypothesis using the independence formula. So I'm hypothesizing that if you are tall, you're more likely to be a middle child. So I'm saying that the probability of being tall, given that you're a middle child, should be greater than the probability of just picking a tall person from the general population. So I think if I narrow my scope to just middle children, I'm going to find a higher proportion of tall people than I am if I just pick from the whole population and try to find out how many people are tall. But we're going to find this out in a minute. So let's test this now. To calculate the probability of someone being tall given that they're a middle child, my denominator is going to be the number of middle children, which there are 40. And of those middle children, 8 of them are tall. And then what's the probability of just picking a tall person in general? Well, there are 20 tall people out of 100 total people in the population. So 8 out of 40, if you divide there, you'll get 0.2. And 2 out of 100 is also 0.2. So it turns out that these are not unequal. 0.2 is not greater than 0.2. 0.2 is actually equal to 0.2. So what we've discovered is that it doesn't matter if I pick from only middle children. I'm going to find the same proportion of tall people in that group as I am if I just pick from the entire population. So what I've proven here is that these two things are independent. Turns out that these things are not related to one another. Now, just so that you see that this works both ways, I could have also tested it in reverse. I could have tested to see what the population is, or the probability is of selecting a middle child from the group of tall people compared to the probability of just selecting middle children. So hopefully you recognize that all I've really done here is flipped these and turned that into an M, right? I've changed this around. Let's calculate this. So of the tall people, of which there are 20, 8 of them are middle children, and the probability of selecting a middle child is 40 out of 100. This is 0.4, and this is also 0.4. This is not a coincidence. These will always be equal. If this one works, then so will this. So it doesn't matter what order you go in, all right? So we can flip these formulas a little bit. What I want to do now is just take a look at these formulas and rearrange them a little bit. So what we've shown is that, in general, the probability of A given B is equal to the probability of A if they are independent. Or I could say the reverse. B given A is equal to the probability of B. And remember, this is if they are independent. So if the events are independent, then these two things are true. Let's dissect one of these formulas just a little bit and just take a look at what this actually means. If I rewrite the probability of A given B, remember, by definition, that means that it's the probability of their intersection divided by the probability of B. Right? If I just rewrite what that actually is defined as, and this is what we discussed in the lesson on Wednesday, the last lesson we did. So what I'm going to do is just a little bit of algebra to get that intersection alone, and just as if these were numbers, I'm going to multiply both sides by the denominator to get that numerator alone. So I'm going to multiply by the probability of B on this side, which is going to allow those to cancel. But I also have to do that on this side. So when I do that, I'm left with the probability of the intersection is equal to the probability of A times the probability of B. And so what I want us to think about is that the formula we can use to prove whether two things are independent can be written any of these three ways. You could use this formula to prove that two events are independent. You could use this formula to prove that two events are independent. Or you could use this formula to prove that two events are independent. They all are the same exact thing. So if you were to go back to the example we did on the last slide, you could have used this formula instead and it also would work. There is no situation where this one will work and this one won't. If you've proven that this statement is true, then you've proven that the two events are independent. You could also do the same thing using these formulas. So in the practice problems and the homework we're going to do, feel free to use any of those formulas.